Okay, here we go. Arc length 8.1. Let's get this derivation done. So we want to approximate the length of this curve. Actually, shoot, we don't want to approximate. We want to go get it, but we're going to start by approximating. So let's go from A to B of our curve y is equal to f of x. And it's already broken down into some nice little intervals of equal length with change in x. And let's try and estimate just one of those little partitions curves. So we just zoom on in and we take a look, and just right here between x sub I minus 1 and x sub I, let's approximate that length with a secant line. And in order for us to go through and to find out how long our secant line might be, well, all we need to do is the old Pythagorean theorem, make ourselves a little right triangle, say a squared plus b squared is going to be equal to c squared. Well, we're going to say that this length right here in blue, we're going to call that thing L sub I. L sub I. Let's jump a second. All right. L sub I is approximately equal to the Pythagorean theorem, or if you want to call this the distance formula, it's all the same stuff. So let's put that in our little L sub I we're approximating for right there. We're going to say it's our change in x squared plus our change in y squared. Oh, let's write change in y sub I, because that can change. The change in x is going to be consistent, but the I can change depending upon the height. So there we have it. Now we're going to want to do a little bit of a substitution. Let's get this all in terms of x. In order to do that, let's go to the mean value theorem. And right above here, I got the mean value theorem set up. And really, this is just the equation of a line and point slope, just written super fancy. So if we want to get our change in yi, our change in y, well, our change in yi, there it is. It's our f of x sub I minus f of x sub I minus 1. Let's call that our change in y sub I. And that's equal to the derivative at x sub I sample point. And the changes in our x, that's x sub I minus x sub I, that's just delta x. So why don't we go and take this and just sub it on in right down there. So we rewrite this. Alright, so our L sub I is approximately equal to our change in x all squared plus, what are we going to square? What's our change in yi? Oh, that's just going to be our derivative of x sub I star times delta x. So let's do a little bit of algebra. We're going to have a delta x on both terms. Oh, delta x squared. So we can actually just take that to the outside. We can just yank it out, and the square root of delta x squared is just going to be delta x. We know for certainty that that's positive. And now once we took this out, we'll be left with a 1 and an f prime of x sub I star squared. Okay, there we go. We now have an approximation for the length of that line, all in terms of x's. And pretty handy. Now, if we want to go through and actually determine the entire length, our entire length, well, let's call this L. L is going to be equal to, well, I believe that's the limit as n tends towards infinity of the sum from I is equal to 1 on up to n of all of those little L sub i's that we just figured out what they were. Well, we've seen this before. This is going to give us our arc length on an interval from a to b, so we're going to integrate the square root of 1 plus f prime of x all squared dx. There it is, our arc length.